Okay, cool. This week, going on with a lot about horizons. Pretty much, first half is just about different types of horizons. Hopefully, the cosmology part is not as fast in pace, so you guys have a chance to catch up and have a go at these. Okay, so for the first question, let me find my pen. Here we go. Okay, explain the difference between the particle horizon and the cosmological event horizon in an expanding universe. So it's just terminology here. Oh, what happened? Oh, never mind. Okay. So, okay, particle horizon first. So this just means a maximum distance from which a signal from the past can reach the observer. So depending on the type of universe you have, like if it's expanding too fast, you might not have a past event horizon, past particle horizon, because anything that's emitted in the past couldn't catch up to you in the expansion rate given. So it's not guaranteed to be there. But for most relatively lower than speed of light, mild expansion, you can expect that there's going to be plenty of events that happen in the past. The light and the signal from that eventually catch up to you, and you can see and like know exactly what happened. So this is just given to you as the co-moving distance by integrating from some initial time ti to the time now from your perspective as an observer. And then you just integrate 1 over the scale factor. And on the other hand, the cosmological horizon, or just called the event horizon, the additional cosmological horizon, just to distinguish it from the black hole event horizon, which is kind of related in concept, but completely different in the way you formulate it. So like to make sure that you don't get confused between two of them. So for cosmological event horizon, it's like the particle horizon idea, but like for the future. So if something is emitted now, how far can it travel in the future? So one way to say is like max distance, a signal emitted now can travel in the future. So this sounds a bit weird because you can't really find that signal again. It's not like you can ask someone like how far this signal has gone. So you sometimes will see like an alternative phrasing of this that makes it a bit more kind of realistic and observable, saying that a signal emitted now, okay, no, that's not a good way to phrase it. Let me try again. So another way to say the max distance away a signal can be emitted now. And still catch up to us. And still like, yeah, I think catch up is good enough phrase. Catch up to you in the future. So it's subtly different. Like they're both signals emitted and trying to travel to you. This one is just slightly different to the particle horizon one, as in like the time of emission. So it's a bit confusing. Like this always confuses me sometimes, because in cosmology, you always say that the further away you look, the further back in time you see. So if you get, it's easy to get that convoluted with this idea to think that like a distance away now is in the past. But no, it's saying that like at this exact moment, the universe already the size it is, how far can I be to emit a signal and in the future it still makes it to me? So the distance away in this sense is not looking back in time as you would think about it in a normal kind of like observing a galaxy far away sense. So those two are easily confused. So I don't know, try your best not to be confused. The formula is very similar. It's just the integration limit's now flipped. So it's going from the time at present to some future time, TE, at the event horizon, and the integral stays the same. Yeah, if you find this definition a bit easy to get lost with this one, then this definition, like maximum distance you can travel to in the future if you emit it from you now, might be like easier to understand, but this might be like kind of more tangible to see, okay, how do you actually know? So it depends on if you care about a philosophical side or actually like a logical side. Anyway, okay, so for part 8 here is assuming the scale factor obeys this power law relationship, which horizon exists? So we just pretty much put this into both of these formulas and see how it turns up. So for the, let's do the particle horizon first. Actually, we'll just do an indefinite integral first with this form of the scale factor. And then we can just sub in whatever integration limits as we need later. So here, just integral dt dash a. So then it's equal to t naught to the n. I can take it out of the front. That's a constant. The t naught is depending on where the observer you are. And so you can pretty much set this to like 1 if you want. But then you can also, but then you still have to integrate the part inside. So t dash to the power of negative n. So that just equals t naught to the n, 1 minus n, t to the 1 minus n. Okay, to ask if a particle horizon exists, you have to go back to like the initial singularity. So like go back to like the beginning of time. At first instance in time, if something was emitted, can it reach me? So in this case, we set the integration limit ti to 0. So we take the limit that we take it all the way backwards to the beginning of time and see if that reaches something. So in this case, I'll get t naught to the n, 1 minus n, t to 1 minus n, and then ti to t naught. So that equals limit ti to 0. And you get 1 minus, no, sorry, 1 over 1 minus n divided by t naught minus t naught to the n, ti to the 1 minus n. Okay, so it obviously depends on the exponent n here to see how this limit evaluates. So it's pretty obvious if n is larger than 1, then this is going to be a negative power. So ti is going to be in the denominator. Then when you take the limit to 0, then your particle horizon diverges. So in other words, doesn't exist. And on the other hand, if n is larger than 0, less than or equal to 1, then this is a finite number. So then it does exist. Although for n equals 1 is a bit of a weird, like a trivial case. So I would say, okay, less than 1, because if n equals 1, then your chi of p is equal to 0. So I don't really know if that's like a meaningful thing to say about the particle horizon. So technically, if n is less than 1, then you definitely have like an actual tangible particle horizon. Sorry. Okay, and following the same thing, we do it for the event horizon now. So pretty much just going through this exact procedure, except for the event horizon, we're asking is sometime in the future. So then rather than taking the limit of time going back to the initial like singularity, we just take it to the future and so take to infinity. How do I get a bit more space here? Move this down. Okay, so chi e is equal to the limit of te going to infinity. Oh, sorry, I saw a question in chat. Doesn't it diverge from 1 by 1% for n equals 1? No, this thing is 0, so you get T naught minus T naught in here. So this like kind of kills it before this thing diverges. I think, yeah, 1 minus n, that's 0. That's 1, T naught to the 1. Yeah, so this, I think that limit exists. My math is getting pretty bad at this point, so don't take my word for it. Okay, so for the event horizon, 1 over 1 minus n, and then this time is T naught to the n, Te to the 1 minus n minus T naught. And okay. And in this case, you, again, depends on what the n is. So if it's backwards now, if n is less than 1 in this case, then this Te is in the numerator. So then when you take it to infinity, then your chi e diverges. So like in this case, it doesn't exist in the sense that you can get to as far as you want. So it doesn't, it's not meaningful to talk about a horizon, because it's kind of saying like the signal you send now will just reach like infinity and beyond. So nothing we can actually say about it. If n is equal to 1, then again, chi e is equal to 0. So again, not that meaningful to talk about it. If n is larger than 1 in that case, then chi e is definitely finite. Then you have a horizon exists. Yep, all good. Any questions? Nope. Okay. Okay, now we're looking at the another case where if the scale factor is this exponential form. So this is called a de Sitter universe. Oof, what is that handwriting? De Sitter universe. And it's really useful. So like it's both the framework for inflation and is also where we are actually right now in dark energy dominated universe. So okay, in this case, the integral becomes just like slightly different, but still fairly easy. So chi is just equal to integral of dt dash e to the minus h t, and that just equals minus 1 on h e to the minus h t. And okay, in this case, now if you want to sub in the for event horizon and the particle horizon, do the same thing. But now for the particle horizon, it's a bit different now, because if you look at this universe, for when ti equals to 0, your a of 0 is equal to 1. So that's not a singularity. And that's kind of like the whole point of like de Sitter universe, is that you don't have a singularity at a particular point in time. So the way for you to like make the scale factor go to 0 to actually turn your universe back in time to a singularity, you actually have to take the initial time to minus infinity. Then this scale factor will then vanish. Then you actually return back to a singularity. So that's kind of like the attractive part of why it's considered the framework for inflation, because you want to shift back the initial time of the singularity to infinitely in the past. So in this case, you do the same thing for particle horizon, but then you have to take the limit of Ti going to negative infinity instead. Okay, and just putting it into the formula here. So you get e to the minus h t naught minus e to the minus h ti. Okay, and in this case, this term minus ti and ti goes to minus infinity, so it becomes e to the positive infinity. So this thing diverges, this thing approaches infinity. So you don't have a particle horizon in a de Sitter universe. And there's nothing you can do about it. That's just like, there's no parameters here for you to tweak. It just happens. So it doesn't matter what the Hubble rate is, it's not going to save you either. Unless your Hubble rate is 0, then in which case your universe doesn't exist anyway. Okay, and for the other thing, it's the event horizon. So event horizon, same thing. So you take the future time to positive infinity. So that's the same. Minus 1 on h, e to the minus h, t e. And then minus e to the minus h, t naught. Okay, now it's going to positive infinity. And so this e to the minus t will kill this term. So the exponential approaches 0. Then this whole thing will then just become e to the h t naught divided by h. So this is also the other interesting part about the de Sitter universe, is that every observer sees like a constant event horizon. So your universe is kind of expanding in the exact right pace that the event horizon in the future doesn't actually move. So that again is a very useful thing for inflation. So that explains the uniformity problem, why the whole universe is actually causally connected. I'm sure Jan's going to go through in more detail in the lectures, but so yeah, de Sitter universes, these two characteristics makes it quite special and is quite useful in explaining a lot of the things in cosmology. Okay, any questions about this? No, all good. Okay. Oh, things moving around. Okay, are there FLRW metric that exhibits neither horizon or both? Okay, so this is a fairly weird question because, okay, so FLRW universes, basically you can think of it consisting of 3 types of matter. So you have, okay, 3 types of energy density. So it could be matter, or it could consist of radiation, or it could consist of the cosmological constant or some kind of dark energy. And okay, the universe could be dominated by one of these 3. So at any given time, depending on how much matter, radiation, or dark energy you have, you potentially could have like enough matter dominating over everything else that you can just treat matter as the only energy density inside the universe, and all of your equations will work out to like a percent level accurate without regarding any of the other types of energy density in the evolution. So the key thing is that if you're in one of these dominated regimes by one of these 3 types, so if you're dominated by matter, then your scale factor solution goes like t to the 2/3. And then if you're dominated by radiation, then your scale factor solution goes like t to the 1/2. And if you're dominated by the cosmological constant, or like another kind of dark energy that satisfies certain things, like your equation of state is not too far away from -1, then it will work similarly. So then your scale factor evolve like e to the ht, like we said in de Sitter universe. So as you can see in this case, we know the horizon of all 3 of these dominated regimes. So whether we're dominated by matter, radiation, or lambda, we can say exactly about the event horizon or the particle horizon. And the universe can transition between these 3, and it does transition between the 3. So it kind of just depends on how you string together these epochs. So for example, in our universe, we're starting off with, okay, we started with radiation, but let's ignore that for now. Early universe is matter dominated, and then it transitions to lambda dominated. So in the early universe, we will have a particle horizon that exists because t to the 2/3 is equivalent to here saying n is equal to 2/3. So then that's less than 1. So then it definitely the particle horizon exists. So at early universe, we have a particle horizon. And at a later universe, when we're dominated by the cosmological constant, then we do have an event horizon because we just showed here that chi-e is constant. So chi-e exists. So then overall, as a universe, both exist. It just depends on when you're asking this question. If you're at early universe, you can find a particle horizon. If you're late universe, you can find an event horizon. So then by contrast, you can also do this thing backwards and come up with some kind of universe where this whole epoch is kind of in a different order. So let's see, like maybe you have some early dark energy model. So like there are some models where you propose that at very early universe, dark energy dominates. So early dark energy domination. And then the universe settles down, the dark energy kind of spreads out, and then you settle into a radiation domination. Radiation dominated. Then in this case, at early times during the dark energy domination, you don't have a particle horizon. Particle horizon diverges. And then when you go to the late time and you want to ask if it's going to be an event horizon, then for radiation domination, t to the power of 1/2, that's less than 1. So your event horizon diverges. So your chi-e diverges too. So in this universe, then like neither exists. Because if you're looking back in time, you're in dark energy domination and you can't find a particle horizon. If you're looking into the future, you have radiation domination and you don't have an event horizon. So in this case, then there are plenty of FLW universes that exhibits both or neither. It just depends on how you want to order these three epochs. So early universe event horizon wouldn't propagate through the radiation dominant phase. Yeah, so because you have to take the limit of your the TE going to infinity, then you kind of you would have like a event horizon while in dark energy domination. But then as you push the time towards infinity, after transition into radiation domination, your eventual answer is no. So yeah, you kind of have to propagate it to the end of time and the beginning of time. So that's what makes it a bit like you only have to look at the behavior of the early one or the late one. Okay, all good. All right, any other questions about the horizon stuff? No, all good. All right. Then let's look at oh man, what is this doing? The Einstein static universe. So consider a universe filled with perfect fluid whose energy density is larger than 0 and the pressure is larger than or equal to 0. Show that no static solution to the Friedmann equation exists in this case. So, okay, perfect fluid. I don't know how much you need to know about this, but then what it means is that your stress energy tensor is diagonal and you just get rho 0 minus p 0 0 0 0 minus p 0 0 0 0 minus p. Okay, and it's a fairly good approximation homogeneously, because if you're in an FLW universe and you're in like the background, you're large enough scales where everything is kind of homogeneous and isotropic, then you kind of are required by isotropy and homogeneity to kill all of the off-diagonal components and have a diagonal symmetric stress energy tensor. So, and that it's like kind of geometrically motivated that your stress energy tensor should look like this. And then people say, okay, this actually looks like a perfect fluid. So it's not saying that we're making the assumption of a perfect fluid. It's just that on a large enough scale, the stress energy tensor tends towards a perfect fluid solution. Okay, so, but the point here is to show that no static solutions exist. So in this case, we look at the two Friedmann equations and we have to argue that A dot equals to 0 and A double dot equals to 0. Oh, like, okay. You argue for these two if static universe exists, if static solution exists. So this is the static solution. So we're going to show that you can't do this. Okay, so for the first one, so that's just the first Friedmann equation. You have A dot on A squared equals to A pi G on 3 rho minus kappa. And if you want static solution, then this left-hand side has to be 0, so it just equals to 0. Then that gives you a solution for the energy density. Rho is equal to 3 kappa A pi G. And since in this case, we know the universe can't be empty, it has to have something in it. So then rho has to be larger than 0. So then this thing is larger than 0. And since everything is a constant, then this implies that your kappa is positive. So we end up with kind of being forced into a closed universe. And this alone already would tell you that it's not possible, because a closed universe always ends up collapsing on itself. So it can't be static if it's going to eventually evolve and recollapse back into a singularity. And we see that the second Friedmann equation confirms that exactly. So for second Friedmann equation, A double dot on A is equal to minus 4 pi G on 3 rho plus 3p. Okay, and here the universe has only perfect fluids with these two conditions. So then that kind of takes out of your hands. This thing is larger than 0 regardless of what you do, unless you say there's nothing in the universe, which is just trivially like not interesting. So in this case, this thing is less than 0, the minus sign here. So you can't really stop, you can't really make A double dot 0. It doesn't matter how you in a like a non-trivial universe. So that means your universe is going to be collapsing on itself, which is exactly what the closed universe would imply. Okay. Is that all good? Any questions? Nope. Okay. Then for part B, now consider a universe filled with pressureless matter and the cosmological constant. Show that in this case, it is possible to find a static solution and find the ratio of the energy density between the matter and the cosmological constant. So yeah, pressureless matter, just any kind of non-relativistic matter satisfies this. So things like CDM, baryons. Okay, baryons on like large enough scales. Neutrinos and black holes. So almost everything that you can come up with to fill the universe with is going to end up satisfying this condition. So it's pretty reasonable to consider this scenario. And cosmological constant is just a simple way of saying you have a negative pressure. Okay, so now you can still do the exact same thing to the first Friedmann equation. So to get A dot equal to 0, then you again get rho is equal to 3 kappa on A pi G. So this is still larger than 0. So it's still a kind of positive curvature closed universe, but you're saved by the cosmological constant, because now if you look at the second Friedmann equation on 3, and then I write out the rho plus p explicitly between the two components, then I get rho matter plus rho cosmological constant minus 3p, plus 3p cosmological constant, and you don't have a pressure for matter, so you don't have to care about that. And then using the equation of state for the cosmological constant, I can then rewrite this in terms of its energy density. Minus 3 rho lambda. Okay, so then in this case here, rho m minus 2 rho lambda, this thing can be equal to 0 quite easily. So if rho m is equal to 2 rho lambda, then the universe is static, because now A double dot equals 0. So if you have sufficient amount of dark energy that's actually pushing the universe outwards to resist the closed universe curvatures collapsing inwards, then you can reach an equilibrium. And so this ratio static then just equals to 2. Okay, now imagine there were small density fluctuations in the matter component of the universe. Describe qualitatively what would happen for a small matter over density and a small matter under density. Okay, so cosmological constant pretty much just stays flat. But matter, it could clump together if it was enough gravity, or from early universe, you can also just have primordials. Or could you explain that last bit again? This bit, yeah. So pretty much I just use the 3p lambda equals -3. So p lambda equals minus rho lambda. So then I get this. So then my second Freeman equation becomes rho m minus 2 rho lambda. And the other condition for static universe is for a double dot to equal to 0. So the only way to do that is for this term to vanish. So then I require the density of the matter component to be twice the density of the cosmological constant. So in this ratio, then the inwards gravitational pull of the matter component is exactly cancelled out by the outwards expansion pressure from the cosmological constant. So the two balance itself out, and it doesn't collapse in or expand outwards. So the universe kind of stays at the right size, the exact size. Does that make sense? Oh, at the density part. Oh, am I cutting out? Hello? Okay. So the density part is just saying rho matter is going to create a gravitational inward force, because you have a lot of matter that's going to try to gravitationally collapse on itself. So it wants to be attracted to each other. And rho lambda provides an outward pressure force. So it's trying to expand the universe outwards. So and so you have one force is collapsing in and one is pushing out. This condition just says that these two forces are equal in this ratio. So then the inwards and outward force are exactly balanced itself. So then the universe doesn't get pushed in or pushed out. So then it exactly kind of stays still. And that's why the second derivative of the scale factor is 0. So then you don't have a force that's changing the size of the universe. Does that make sense? It's just thinking about, yeah, it's just thinking about the inwards and outwards pressure versus gravity. Right, no worries. Okay, so what this is saying is like on average in the universe that you have gravitational force that exactly balances out the outward pressure force. But if the matter component starts gaining fluctuations, then it becomes slightly problematic for the balance, because if you imagine the universe here as a whole, and I have here this patch that has like more matter than usual, then what happens is that around this part, the inward gravitational force, because the more mass you have, the larger the gravitational attraction is, then the inward gravitational force is larger than the outward pressure force, assuming the cosmological constant is evenly spread out across the universe. So then the outward pressure is the same everywhere, but now in this part, the inward gravity dominates. It doesn't even have to dominate, actually. It just has to like kind of, the inward gravitational force just has to slightly overpower the outward pressure force. Because now what happens is that if you're able to slightly overpower the outward pressure, then you're able to start attracting more matter towards you. So like patches around here on the outside, in the outskirt, they might be just normal density, but then they're seeing this extra gravitational force in this local region, and they also get attracted towards it. And then this kind of becomes like a rich gets richer kind of scenario where one part with overdensity starts attracting the surrounding parts towards it, and then it gets denser. And as it gets denser, it's even stronger gravitationally. So then it's able to attract more and more materials. So then it kind of accretes inwards. And if the outward pressure stays constant, so the cosmological constant is the same everywhere, then you're never able to actually bring the balance back, because it's the inward force is going to get stronger and stronger, and the outward force never gets stronger to compensate. So in the case that you have an overdensity, whereas and any local region that you have more matter than usual, then the universe is going to start kind of snowballing towards that part and kind of cascades, and eventually the whole universe will collapse into that position. So if this is larger than static, local gravity overcomes pressure. Oh, got a question. Like tapping a superheated fluid. Yeah, pretty much. It's just like because you don't have a restoring force that to balance it out. So once it kind of gets going, it's just gonna keep there's nothing stopping it. So local gravity overcomes pressure and starts accreting surrounding material. And okay, imagine this kind of cascade, and eventually the whole universe collapses in. Okay, but this is one local overdensity, but on the underdensity part, then it's just the same story, but like the opposite direction. So if you have this one part with less matter than usual, then with less matter, that means the inward gravitational force is weaker and the outward pressure force is the same everywhere. So then now that means the outward pressure force actually dominates. So then the matter that's around this region, so the matter particles or like the fluid that's around here, they get blown out by the outward pressure force because the inward gravity is not enough to hold them together. Then as you get blown outwards, you become even less concentrated. So it becomes even more rarefied around this region. So this void kind of gets less and less. And that means the pressure force is going to get more and more dominant over the gravitational force. And this eventually will just means that this void will get to expand. And okay, this scenario might be a bit more complicated because you have to be careful that the outward expansion doesn't happen so quickly that you kind of collapse the. So if you imagine matter is on like average density everywhere else around it, and it's just low density here. If the outward expansion is fast enough, then you could potentially bunch up the matter in a ring around this void. And in this ring around the void, this part will be overdense. So then you end up with this scenario surrounding the void region. So it's if this happens too quickly, it also would have a problem. But then if you assume like a fairly small underdensity, so then the outward pressure kind of slowly starts spreading the matter outwards, then it kind of has enough time to spread out the matter across the entire universe and then eventually rip apart this part of the universe via this hole. Wouldn't the overdensity produce area of underdensity by sucking matter? And would there be explanation for this? Yeah, so again, it's about the rate of that happening. So if you're sucking matter from your surroundings, then what that means is that you have to ask how quickly are you sucking matter into the overdensity compared to the next patch replenishing the patch that you are taking from. So for gravity is rather weak. So then the process kind of happens really slowly. So then the next part of the universe will then have sufficient time to kind of replenish the, it's going to come inwards together with, to replenish the surroundings, and then you keep taking it. Whereas if you somehow have a sudden overdensity that's able to kind of very quickly drag all the matter inwards, then yeah, you will actually end up with voids in between high density regions. So it all depends on the quick how fast you're able to accrete and disperse material compared to the rest of the universe. So yeah, like in reality, like if you look at the actual universe, you see there's going to be plenty of high density regions that are kind of like filaments, and then in between them you have all these low density voids. That's because all the matter has been sucked towards these high density filaments and then left with low density voids in between. So in reality, yeah, you will have something way more complicated. But if you're thinking about like a very slow gradual process just in the local area, you can think of it as kind of rich get richer, dragging everything in, and this one's like poor gets poorer. You start blowing things outwards, and then you have a faster blowing rate, and then it kind of just keeps going. So yeah, that's for this part, and that's for this part. So yeah, you can say that voids grow as it blows matter outwards and thus increasing pressure. Okay, so the kind of takeaway message from these two like kind of local scenarios to consider is that the Einstein static universe is actually extremely unstable. You have to maintain an exact homogeneous equilibrium between the gravity and the outward pressure force to keep it static. If there was any kind of perturbation in either direction, whether it's an overdensity or underdensity, then you see very quickly the situation cascades and it will evolve to a different universe. So the static nature is not guaranteed. It's kind of like only exists in a very perfect condition. And it, in the real universe, we know that there's a lot of quantum fluctuations. And in the early universe, the inhomogeneities, these overdensity, underdensities are imprinted in the universe from the very beginning. So there's no way for you to actually achieve a kind of balance. And you're bound to have these local collapses and local voids. And that's exactly why we see like the large scale structure today. And yeah, that's all the questions for this week. Any other questions or problems? If not, then I'll upload the solutions to last week's tutorial. I'll upload these next week. And yeah, I'll get the next week's problems up as soon as possible as well. And yeah, I'll see you guys later then. Or I'll be here for another 10 minutes if you have any other questions.